So the topic for this lecture is electric potential due to a system of charges. Now, as we know that electric potential is a scalar quantity. So suppose there are four charges which are placed at four different places. Suppose Q1, Q2, Q3, and Q4. And there is a point P at which we have to find the potential. So what we have to do is we have to find the individual distance R1, R2, and R4 of this point from all the individual particles. Now, as the distance from Q1 is R1, so the potential will be due to Q1, it will be K, Q1 by R. Then due to Q2, it will be Q2 by R2. Then due to Q3, it will be K, Q3 by R3. And due to Q4, it will be K, Q4 upon R4. So we have to simply add all these potentials to get the total potential. This is a question which says that 3-point charges Q1 is equal to 1 microcoulomb, Q2 is equal to minus 2 microcoulomb, and Q3 is equal to 3 microcoulomb are placed at 1, 0, 0, 0, 2, 0, and 0, 0, 3 respectively. Find the electric potential at the origin. So first of all, we will just draw a diagram. This is the x-axis, then y-axis, and the z-axis. And there is a point 1, 0, 0. And there we have a charge q1. Then there is a point 0, 2, 0. Here we have a charge q2. And then there is a point 0, 0, 3. So 1, 2, and there is a charge q3. There is the point where we have to find the potential. So this distance is 1 meter. This whole distance is 2 meters. And this whole distance is 3 meters. So the potential will be simply K into Q1 is 1 microcoulomb, so 10 to the power minus 6 divided by 1 plus K. Q2 is minus 2 microcoulomb, so it is minus 10 to the power minus 6. This is K. Q3 is 3 into 10 to the power minus 6 divided by 3. So we will solve it. So this first term will be 9,000. Then second term will be minus 9,000. And third term will again be plus 9,000. So as we can see, the total potential will be 9,000. So this is another question. In the given figure, the figure is in front of you. There are 4-point charges placed at the vertices of a square of side A is equal to root 2 meter. If Q1 is equal to 18 nanocoulomb, Q2 is minus 24 nanocoulomb, Q3 is plus 35 nanocoulomb, and Q4 is plus 16 nanocoulomb, then find the electric potential at the center P of the square. Assume the potential to be 0 at infinity. So this is, they have taken the reference at infinity. So what will happen is, this is A, each side. Now, as we can see, that this distance of any particular charge is half of the diagonal. The whole diagonal can be found out using a root 2. So half of diagonal, which is this distance, a root 2 divided by 2, which means it is e. Now from each charge, the distance is a upon root. So the potential at the point P will be k q1 upon a by root 2 plus k q2 upon a by root 2 plus k q3 upon a by root 2 plus k q4 upon a by root 2. So we can take root 2 at the numerator, then a we can take common, a also we can take common. So we will get q1 plus q2 plus q3 plus q4. Now we can see that the values are given. So it will be root 2, k will have 9 into 10 to the power 9 upon a. A is root 2 and q1 is 18, q2 is minus 24, q3 is 35 and q4 is 60. And all these are in nanocoulomb, so we will multiply 10 to the power minus 9. So we can cancel it and we can get 10 to the power 9 and minus 9 will also get cancelled. 9, 18 minus 24, it is minus 6. Minus 6 plus 35, it is 29. 29 plus 16 will be 45. 45 into 9 will be the answer. So 9 5s are 45 again. 9 4s are 36 and 405 volts. So we can see another question. This question says that suppose that 3-point charges QA, QB and QC are arranged at the vertices of a right angle triangle as shown. The figure is given to us. What is the absolute electric potential at the position of the third charge if QA is equal to minus 6 microcoulomb, QB is equal to plus 4 microcoulomb and QC is equal to plus 2 microcoulomb? They have also given A as 4 meter and B as 3 meter. So we have to find the electric potential at the position of the third charge. So at the position of the third charge, the electric potential will only be due to the other two charges, which means that the potential at this point C, we take it as C, it will be only due to QA and QB. So what we can do is potential due to QA can be written as K. Then the value of QA is minus 6 into 10 to the power minus 6 because it was minus 6 microcoulomb and divided by the distance was C. So C in this case will be 5 meters. If we solve it, the potential due to QA will be 9 into 6, it will be minus 54 and then there will be 3 zeros divided by 5. So it will be minus 10800 volts potential due to QA. Then the potential due to QB, it will be Q. QB, the value of QB 4 microcoulomb. So it will be 4 into 10 to the power minus 6 divided by the distance of QB from this point C is B, which is 3 meters. So if we solve this, 3 4s are 12, and it will be 12,000 volts. So the total potential at the point B will be the algebraic sum, which means 12,000 minus 10,800, the net potential. So the net potential is 1,200 volts. So let us come to one more question, which says that the charges, each capital Q, are placed at x is equal to d, 2d, 4d, and so on to infinity. Find the electric potential at the origin. So I am going to draw the diagram here. Suppose this is the origin. At x equal to 0, this is the origin. Then B, 5, 6, 7, and 8. So one charge they have placed here at D, then one more charge at 2D, then one more charge they have placed at 4D, then one more charge they will place at 8D, and so on. They will place at all the different points in multiples of 2. We have to find the potential at this point. So the potential at this point will be the algebraic sum of the potentials due to the individual charges. So it will be Q upon D plus K Q upon 2D plus K Q upon 4D plus K Q upon 8D, and so on up to infinity. This will be the net potential. So the potential will be, like, we can take K Q upon D as common. So it will be 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 up to infinity. So this is an example of an infinite GP. So an infinite GP, as we know that sum of an infinite GP is given by A upon 1 minus, where A is the first term and R is the common ratio. So the potential will be K Q upon D. We can see here that the first term is 1 and the common ratio is 1 by 2. So it will be 1 upon 1 minus 1 by 2. So V will be equal to KQ by D, and 1 upon 1 by 2, which gives us, so potential will be 2KQ upon D. So here is one more question. It says that a charge capital Q is placed at each of the points x is equal to D, x is equal to 3D, x is equal to 5D up to infinity, and a charge minus Q is placed at each of the points x is equal to 2D, x is equal to 4D, then 6D, and up to infinity. So we have to find the electric potential at the origin. So first of all, let us draw the diagram for this. So I will make it like D, 2D, 3D, 4D, 5D, 6D, 7D, and 8D. Suppose I have taken up to 8D. And this is the origin. This is the point at which we have to find the potential. So at the points odd numbered points, there is a charge q. Then again there is minus q. Then again q. Then minus q. Then again q. Then minus q. Then again q. Then again minus q. So in this way we have different charges which are placed, and this continues up to infinity. So the potential will be, we can see that it is k q upon d. Then minus q is placed 2d distance apart, minus kq by 2d, then plus kq by 3d, then minus kq by 4d, and so on up to infinity. So if we take k, q and d as common, we will get 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and this will go on up to infinity. Now this series 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, this is an expansion of log 2 to the base e. So the answer will be kq upon d and log 2. So this will be the answer. This is all about electric potential due to a system of charge.